All right, so energy is measured in calories. That's got 0 calories.
I have a question. So, joules and calories, there's 4,186 joules and calories.
Yep.
Is it a capital C or a lowercase c?
Big C.
Big C.
All right, so if we have water in a lake, it doesn't have any potential energy. Water doesn't really have much chemical energy. It's actually got lots of nuclear energy, but we don't know how to harness it. We can get it started, but we can't stop it, so we don't use it. If we add energy to water, we can store it up in a tank. So if you go over there by Sugar Creek, there's a big, huge water tank up there, right? It's got water stored in it, and the water is stored there so that it has lots of potential energy so that it can flow and squirt out your pipes even if the power's off. Okay, so we're storing energy in case we ever need it for an emergency. In lab, we talked about the fact that power is the rate that energy is transferred, right? When you were running up the stairs, just like lifting water up to a tower, you were lifting Kyle up to the top of the bleachers, right? Once Kyle or the rest of you were up there, if we had a cool slide like the Children's Museum, right? What's that slide called? Christmas time, the slide, the Children's Museum.
Children's Museum slide.
What?
The
Children's Museum. You guys have all been on it. You can slide down and turn your potential energy to kinetic energy, and Kyle will be going whee at the bottom really fast, right? And then he could slide on the carpet and turn it all into friction and heat and do it all over again. But you figured out how much work you did by taking the mass that you lifted times g times the height, right? That was the work you did. And you divided it by the time. So the work divided by the time tells you how the rate at which you were converting energy. How many joules every second your muscles were converting, right? By the way, if you're having trouble in the last problem, the push-up problem, you got to take 2/3 of your mass times g times h times the number of push-ups you did. That's the work. mgh is the potential energy of one push-up, but you didn't lift your whole mass unless you're doing push-ups upside down. If you're just doing a regular push-up, you're lifting about 2/3 your mass. So take 2/3 of your mass times g times h, that's for one push-up, and multiply that by the number of push-ups you did, and that'll tell you how much work you did. Then take your work divided by the time, and that will tell you your power. Okay? So this is our last equation in our toolbox. So take a minute and put it in your toolbox, flip to the back of your book. You already have PE, KE, total energy, mechanical energy, and you have the work energy theorem. That's the big idea. The last thing is this, and it's useful to note the units that are required. Because if you get a problem and they are not in these units, you're going to have to convert. For example, P is power. It's got to be measured in watts. The work is the energy transferred. It has to be in joules. If some goofy dude gives you the problem in calories, what are you going to do? Convert to joules. T is the time. It's got to be in seconds. If somebody gives it to you in minutes or hours, you're going to have to convert to seconds, right? So, I know this is a little confusing. What is this right here? No, it's not watts. It's the work. It's the work. W is the energy transferred, the work. And it's measured in joules. So this gets confusing, I know. The work is measured in joules. What is power measured in?
Watts.
See, there's a W here, right? You see W, you think watts. But that's not true. W in the variable is a work. Okay? P is the power. The units of power are watts. The units of work are joules. Okay, so make sure you don't just see W and automatically think watts. If it's in an equation, W is the work. If it's after a number, then it's watts. It's joule. It's power. Okay? All right, so what we're going to do is we're going to solve problems with this. The standard unit of power is 1 watt, and a power of 1 watt means you are transferring 1 joule of energy every second. Okay? So where have you guys seen the word watts before?
Battery.
Batteries? Light bulbs. I don't think batteries.
don't know.
So, we're talking about batteries, light bulbs in a second. The standard unit of power is a watt, but that's not the most common unit. If you are measuring the power of a lawnmower though, perhaps you might use, or cars, you probably use horsepower, right? So, another unit of power is the horsepower, and this is a really handy conversion to jot down in your conversions. If somebody gives you the power in horsepower, that's equal to 1 horsepower is 745 watts. So that goes in your handy conversions, where you have how many miles in a meter, how many seconds in an hour. What else you got in there? Got some goodies. 1 horsepower is 745 watts. We'll use that in a little bit. Why is it called a horsepower? Well, back in the old days, how did you transfer energy? You used a horse. You probably actually used a mule. So if you were a miner in England in the 18th century, you loaded up an ore cart, and a horse attached to a rope with a pulley would pull that mine cart with its load all the way up to the surface. So the mule was transferring energy from its oats or whatever it eats to the potential energy of the ore cart. They'd unload it, lower it, and they'd lift it again. So along comes this new machine. What's the new machine called? That replaces all the horses in the mines. Not yet. Almost. It's called a steam engine. And if you're trying to sell a steam engine to a guy, what are you going to do? How are you going to make it sound good? Say, hey man, this steam engine, 10 horses. It does the work of 10 horses. So we compared the new thing, steam engines, to the energy transfer rates of the animals that people are used to. So you could buy a steam engine that had 10 horsepower. It could transfer energy at the same rate as 10 horses. Okay? And so we still use horsepower to measure engines. Cars, trucks, lawnmowers, and stuff like that. Okay? If you're exercising, you might see your power measured in calories per minute on the little readout of the elliptical or whatever you're on. So that's another way. So in general, any energy divided by time is a valid unit of power. Put your computer there, guys. That way I won't be distracted. All right. So talk about light bulbs for a minute. 100-watt light bulbs. That means you get 100 joules every second being turned from electricity into what? Yeah, you wish it was light. Turns out if you got a 100-watt light bulb, only 8 joules gets turned into light. What do the other 92 joules get turned into? Heat. You guys raise chickens when you're in 5th grade? What did you do to keep the box warm? You put a light bulb in there. Is that because the chickens need light? No, it's not a light bulb, it's a heater. Right? Light is a byproduct, only a small amount. So that requires you to waste 100 joules of energy every second to get some light. We measure light in lumens. You can get the exact same brightness of light for only 23 watts if you use a compact fluorescent light bulb. You still use about 8 joules of energy getting light, but the rest of the energy, which isn't as much, goes into heat. So they aren't nearly as hot. And then you can do even better. Now, this is 2 years ago. Nowadays, we're down to about 13 watts. So you can get 8 watts of light, or 8 joules of light every second, and only waste 5 joules of heat every second. So that's much more efficient. What's the bad part? What's the downside? How come every single bulb in the world is an LED right now? What does this cost? 25 cents. These are like 12 bucks. So replacing all the light bulbs in your house with LEDs would cost a fair amount. But it saves a heck of a lot of electricity. We can calculate it, but not now. A little later. Let me solve 2 example problems. I got a lawnmower, and my lawnmower can do 14 million joules of work during the hour I'm out there pushing it. By the way, work means transfer of energy, right? What kind of energy gets transferred in a lawnmower? From what to what? What do you think, Henry? From what kind of energy goes into your lawnmower? Definitely not Monster, right? We already know it has no energy in it. Fuel, gasoline, and what kind of energy comes out of it?
No.
Kinetic energy. The point of the motor is to spin the blade, right? Now, once it gets the blade spinning, that blade keeps smacking into grass and slowing it down, and so it's got to keep working to keep it spinning, right? So it's converting chemical energy to kinetic energy and probably some heat and probably some sound, too. That's a form of energy. All right? Okay, so 14 million joules. What is that? Is that the power, the work, or the time? What do you think, John? It's the work. It's the energy transferred, right? How do we write million, by the way, mathematically?
6 zeros.
Think about metrics prefixes. One of them means a million. Rose?
10
Kilo? Does kilo mean a million?
No, it's mega.
Kilo means 1,000.
Mega.
Mega means a million. So 10 to the 6th. So, the work we do is 14 million joules. You can write million as 10 to the 6th. Here's where I said watch out. How long do we run our lawnmower? 1 hour. But what units do we need for time? Seconds. So I put 3,600 seconds. So now, without a whole lot of effort, you could grab your calculator. You could take the power is the work divided by the time. You can take 14 times 10 to the 6th divided by 3,600, and you can get the power of about 3,900 watts. So if you go to Lowe's and look at lawnmowers, you could say, hey, you got a 4,000 watt mower? No? You're not doing that? What would you rather know, Cooper?
Horsepower.
Horsepower. Can we convert that to horsepower? Do you have a conversion factor? Do it. Convert it. Convert 3,900 watts to horsepower. What, you divided? Why did you multiply? Why? You multiply or divide, guys? Because half of you are just guessing.
Divide.
How do you know? Because you show your factor label method, right? If you start with 3,900 watts, you need watts on the bottom to cancel the watts. That's why you divide. So take 3,900 times 1 divided by 745. It's a 5.2 horsepower push mower. Okay?
Is that good?
That's just a push mower.
About 5 horses and a little.
My John Deere ZTR is 22 horsepower.
22 horses. That's.
It can transfer energy at the rate of 22 mining animals.
I don't know.
So you still use that
I think 22 mules can do better.
I don't know. All day long. My mower can run all day long. Gotta rest your mules.
Feed 'em.
I don't know. All right, second question. So, Cooper there, he's got to dry his hair in the morning.
Not me.
Takes him 8 minutes with the hair dryer to get that look. I know you guys don't believe it, but
At least.
at least. How much energy does Cooper use drying his hair in the morning if his hair dryer is 1,800 watts and it takes him 8 minutes to get just the right look? So here's where it gets confusing, guys. Everybody sees that W, and what do you think that is? Work. It's not. It's W, and it follows a number, so it is a unit. What is this quantity right here? It's the power. It's the power. The power is 1,800. The time is what? 8 minutes. Darn it.
480 seconds.
Take 8 minutes times 60. 60 seconds in a minute. 480. Is that what you said, Devin? 480. There you go. Okay, go ahead. See if you guys can find the energy transferred. How do you find the energy transferred? The power is the work over the time.
So you multiply.
So find the work, the energy transfer.
Power times the time.
Do it. Got it, Chris? What do you got?
3.75.
What?
3.75.
Yeah, 14,400.
I got 864,000.
That's what I got.
If the power is the work over the time, then the work, get the work by itself, you gotta multiply both sides by t.
I didn't put it in.
The power times the time is the work.
How'd you get 3.7?
1,800 joules every second. That's what Cooper's using up. 1,800 joules every second times 480 seconds. So, that's a lot of energy there, Cooper. Is it worth it?
Yes.
All right, it's worth it. What does that cost his dad?
How much that cost?
Well, it turns out that we measure energy, electrical energy, in a goofy unit called a kilowatt hour. A kilowatt hour is a unit of power times a unit of time. Kilowatt hour. Unit of power times a unit of time is actually a unit of energy. So a kilowatt hour is 3,600,000 joules. That's a kilowatt hour. And Duke Energy charges you 10 cents, 0.10, 10 cents for each 3.6 million joules of energy they deliver to your house in electrical form. So if you want to know how much this costs, you got to do a little conversion, and it looks like this. 3.6 million joules costs 10 cents. So you take your energy, 864,000 joules. 10 cents is the same as 3.6 times 10 to the 6 joules, but you want to cancel joules. That's how you know that goes on the bottom. Take this times 0.1 divided by that, and you get $0.024. Or, how much, Cooper?
Not sure.
2.4 cents. Costs 2.5 cents to dry his hair in the morning. That make sense? No pun intended? Okay, you're going to solve some problems now. Before you do though, the first 3/4 of the problems are easy like this. The last 2 or 3 get a little harder. I just want to show you. What would happen if you had a problem like this? Find the power needed to get a truck moving. To find the power, you need the work and the time. Do you have the time?
Yes.
Do you have the work? No. When you get to the end, there's a couple of problems that are 2-step problems. You are going to have to use the mechanical energy at the end equals the mechanical energy at the beginning plus the work to find the work.
So that would
Once you've done that, then the power is the work over the time. So the last couple problems involve finding the work, like we did last homework, and then using it to find the power. And I've got an example of that, it's here, but I don't want you to worry about it right now until you get there. So when you look at the example problems and you get to the ones where it's like a truck accelerating and wants to know how much power, you can look at the example, it's posted, okay? But I don't want to confuse you yet. So go ahead and solve the first 3/4 of the problems on the homework 3, okay? I'm done. Do you need a diagram? Do you need oxygen?
Yeah.